Have you ever really stopped to think about how a machine learns to see? I don't mean in a big, flashy sci-fi movie kind of way. I mean, how does it learn to recognize something as simple as a number you just scribbled down? Well, today we're going to pull back the curtain and see exactly how it's done.
Okay, so look at this. You and I, we glance at this and we know instantly that's a 3. It's second nature. But for a computer, which doesn't have eyes or a lifetime of experience with handwriting, this is a huge puzzle. How in the world does it figure this out?
Well, I can tell you, it's not magic. It's something called a perceptron. And it's actually a beautifully simple and really powerful idea. So in this explainer, we're not just going to talk about it. We're going to build one, right here, piece by piece, so you can see exactly how it thinks.
So, what is a perceptron? Just think of it as a tiny little machine that can only make one simple decision. Yes or no. That's it. It's the most basic unit, kind of like a single Lego brick of those giant structures we call neural networks. All right, first things first. Before our little machine can make any decision at all, it needs some information to work with. It has to see the number. But, computers don't have eyes, so how do they do that? The whole process starts with this number right here, 784. Now, I know what you're thinking. What on earth does 784 have to do with recognizing a 3? It seems totally random, right? Well, it's the number of pixels in the image. The computer takes that 28 by 28 pixel image of the 3 and breaks it down into 784 individual data points. Each one of those pixels is an input, with a value telling the computer how bright or dark it is. That's the raw information our perceptron gets to see. Okay, but here's the thing. Not all of those 784 pixels are created equal, right? Some are way more important for figuring out if it's a 3 than others. So our machine needs a way to know which pixels to pay attention to and which ones to ignore. And it does this with something I like to call importance dials. In machine learning, these dials are called weights. Every single one of those 784 pixels gets its own special weight. It's just a number that tells the perceptron, hey, pay close attention to this pixel, it's a big clue. Or, meh, this one over here, you can pretty much ignore it. So as the machine learns, it starts to turn up the dial, assigning a high weight to pixels that light up right along the curves of a typical number 3. And at the same time, it turns the dial way down for pixels in the corners that are almost always empty. It's literally learning what parts of the image matter and what parts are just noise. So we've got our inputs, we've got our importance dials or weights, but there's one more really critical piece of the puzzle we need to talk about. It's called the bias. The best way to think about it is as a sort of starting hunch, a default setting for the machine.
And to see why this is so critical, just ask yourself this. What happens if we show our perceptron a completely blank image? I mean, nothing there. All 784 of its inputs would be 0. Without some kind of starting hunch, what's it supposed to do?
This is where you really see the difference. Without a bias, a totally blank image leads to a total guess, a 50-50 coin flip. Not very smart. But with a negative bias, our perceptron has a built-in default belief. It can look at that blank image and say, I see absolutely nothing, so I'm really confident this is not a 3. See? It's already much smarter. So really, the bias just acts like a little nudge. It's telling the perceptron, look, even before you see any evidence from the pixels, this is my starting point. I'm either generally inclined to say yes, or in this case, generally inclined to say no. All right, let's get to the final step, the part where the decision actually gets made. We've added up all our weighted inputs, we've added in our bias, but what we have now is just a raw number. We need something like a brain to interpret that score and make the final call.
So let's just say, after all that math, multiplying the inputs by the weights and adding the bias, our machine spits out a raw score of, say, 12.3. What in the world does 12.3 even mean? Is that a yes? Is it a no? It's not a useful answer. We have to translate it into a clear, confident decision.
And that is the job of the activation function. For this, we often use a clever little function called sigmoid. And all it does is take any number you give it, big, small, positive, negative, and it squashes it into a nice, clean value that's always between 0 and 1. It turns that raw score into something that looks a lot like a confidence score.
So, our raw score of 12.3, after we run it through that sigmoid squashing function, it becomes this, 0.999995. Now that is an answer we can work with. It's basically as close to 1 as you can get. Our perceptron is practically yelling, yes, I am overwhelmingly confident this is a 3.
And there we have it. We've got all the parts. Our inputs from the pixels, the weights or importance styles, the bias or starting hunch, and the activation function that makes the final call. Let's put it all together and watch it work one last time.
So here's the play-by-play. First, the 784 pixels go in. Each one gets multiplied by its own importance style, its weight. We add all that up, and then we add in our starting hunch, the bias. That final number gets pushed through our sigmoid squashing function, and out comes the final answer, maybe a 0.96. The perceptron's decision, yes, I'm 96% sure this is a 3. So let's just quickly recap those two big ideas. The bias. That just gives the perceptron a default answer, a starting point so it doesn't get confused when there's not much evidence. And the activation function? That's what turns a messy, raw score into a clean 0 to 1 probability, which is absolutely crucial for making a clear decision.
So why should you care about all this? What's the big takeaway? It's that these individual, simple ideas come together to create something incredible. The weights let the machine learn what to look for. The bias gives it a sensible starting point. The activation function lets it make a confident call. And altogether, they allow a very simple machine to actually learn from experience. So, we've done it. We've built a single, tiny perceptron that's gotten pretty good at spotting the number 3. But that leaves us with one last, really interesting question. If this one little machine can only do this one job, what would it take to build something that could recognize all 10 digits, from 0 all the way to 9? Now that is where things start to get really cool.